Alright, hi guys, I'm James, and today we'll be doing a physics lesson. I think this is meant to be more of a trial lesson for you guys to just get familiar with how we go about teaching in our lessons. So what I think I'll try and do is that I want to make things more intuitive and more fun. So instead of focusing so much on like the math and then like memorization of formulas and everything, I want to just give you guys a more complete understanding of how the concepts in physics work. Like how like instead of simply knowing that they work, more about like all the background, like how these concepts work and why they're able to work in different scenarios, as well as how these like different concepts all tie together to create a very kind of complete physics picture. So that's something I want to try and achieve with you guys, and I hope that my lessons will be able to do that. If you guys have any feedback after this lesson, do feel free to contact us. We'll be more than happy to listen to what you guys have to say, and we will change our teaching accordingly. All right, so for today, what we'll be doing is kinematics. It's one of the more fundamental topics. It's quite crucial for everything else that we're doing in physics afterward, like dynamics, statics, rotational motion, and everything else. So basically, what this topic is about, is that it studies motion. Very simply, it's just about how objects move. Like let's say like how a car can accelerate from rest to reach some velocity and travel some distance, or like how a ball falls under gravity to hit the ground. Like these sort of examples are what kinematics is about. It's simply about studying motion without being concerned about why the object moves or like what causes it to move. So in kinematics, we have a few crucial quantities that we are going to discuss. So we have displacement. Sorry. Um, we have displacement. We have velocity, and we have acceleration. So these are our three kinematic quantities. And basically, in the discussion later, we will be focusing on how these all relate to each other and how they affect each other. So that will be our focus for later. But for now, we need to first define a few things. Firstly, it's very important in kinematics to understand the idea of a vector. So what is a vector? You might be asking. A vector is basically some quantity which has both magnitude and direction. So what does this mean? Usually we can visualize vectors as arrows. So these arrows basically, they have some length, right? They have this length, and their length corresponds to the magnitude of the vector. So if a vector has, let's say, magnitude of maybe like 5 units, right? Let's say it's a magnitude of 5 units, then geometrically we can represent this as a vector, as an arrow of a vector with a length of 5 units. That should be quite intuitive, right? And as for direction, basically the direction will be the direction that the arrow is pointing in. So let's say we define this to be leftwards, right? Basically it's like a horizontal direction and this is pointing leftwards. And maybe let's say that this angle is 40 degrees. So what we can say about the direction is that this vector is pointing at 40 degrees. In this case, it's this way. So it's anti-clockwise to the leftwards direction. Yeah, so what we can do is that we can use these sort of angles to define the direction that your vector is pointing in. Like imagine a compass, right? The compass, like it has like the north, south, east, and west directions, and your compass arrow can point at any angle along this circle. So that's basically what like this vector is. that we define a length first, we give it a magnitude. Then afterwards, we constrain the vector to point in only one direction, and that would be a fully defined kind of vector with both magnitude and direction. So the idea of direction is very important. Like if our vector has like the same magnitude but points in a different direction, that's like this, then these two things are different. They're not the same because they point in different directions. So therefore, their vector is different. And this idea is quite crucial in kinematics because we have to distinguish between a vector and scalar values. So a scalar is basically something that only has magnitude. And in kinematics, where do we see this contrast? Basically, in kinematics, what we observe um is that our wait, right. Basically, in kinematics, what we observe is that we have two types of quantities, which are vectors and scalars. So one example of a vector quantity will be displacement. And what is displacement? Displacement is simply the change in position. So let's say we have an object initially at this point O, and it moves towards some new position. Let's just call it A. So our displacement will be the vector that points from O to A. So this will be our displacement vector. But in contrast, scalars like distance is actually a scalar. So what is distance? Distance will simply be like very intuitively the length. So like this length here between O and A is a distance. And this isn't concerned about your direction or like your magnitude. Like it isn't concerned about the direction of your displacement. It's only concerned about the magnitude of the length of displacement. And that's basically our distance. And we will observe in kinematics that actually many quantities are vectors. So your velocity is a vector, your acceleration is a vector. And why is that so? Because your velocity, right? Your velocity, you can imagine that your object is moving in some direction. Let's say your object is moving towards the north. Then we will say that the vector of the velocity is pointing towards the north because there's a direction associated with the velocity. But speed is different. Because for speed, right, let's say you have a car, the car is traveling at 90 kilometers per hour, then that is the speed. But we aren't defining the car to be moving in any direction when we talk about the speed of the object. So therefore, this is the difference. Like for kinematics, we usually deal with vectors because these are more complete. They give us more information about the object. They tell us like how like which direction is moving in, how fast it's moving in a direction, and also for displacement, it tells us the relative position of the object, both in terms of the distance and in terms of like where it's positioned relative to this object, relative to the initial position. And so that's our definitions of vectors and scalars. Okay, and now we have to do some mathematics. So we've talked about the idea of vectors having both magnitude and direction, but um, we have yet to really like do any kind of calculations regarding these vectors. So here's an example. Let's say I have a boy, right? I have this boy here, which starts at point O, and initially this boy moves in some direction. Let's say it just moves in this direction, and the boy travels a distance of 4 meters. Then afterwards, this boy, right, he changes his direction of motion to a direction that is 60 degrees from his initial direction of motion. So he now moves in a different direction and he moves a distance of, let's say, 5 meters. So initially he moves 4 meters and now he moves 5 meters, right? And so the question is, what is the final displacement of this boy with respect to the initial position, O? So let's call this one A. So basically it's telling us to find the vector OA. So how do we do this? Of course, we can't say that the displacement, like, or the magnitude of the displacement is 9 meters, right? That's incorrect. Because if you draw this out geometrically, if you just draw this line out, it's quite clear that this line has to have like a smaller length than the sum of these two vector lengths. Because it's a triangle, right? Like if you think about it, like triangle inequality, your like the lengths of any two sides summed together cannot be smaller than the length of the third side. And so therefore they must be at least larger or equals to. And because mm, your vectors are like pointed at an angle to each other, therefore like um your final vector will actually be of a smaller length than the sum of the two lengths of the individual vectors. And so therefore the answer definitely is not 9 meters. So how do we do this? Mm, Basically, it's just a lot of math. What we do is that we use the cosine law. Um, which basically states that let's just say we have a random triangle, lengths A, B, C, and some angle theta. So basically, the cosine law relates these lengths and the angles together, saying that A squared equals to B squared plus C squared minus 2 times B times C times cosine of the angle between these two sides opposite this side. So this is our cosine law. And now with this in mind, we can actually solve the question. So here, what we have is that your B is equals to 4, right? Because like that's your initial vector length. And C is equals to 5. That's your second vector length. And A will basically be the vector summation. So mm, your vector over here, the vector OA, we can say that this vector is a vector summation of two vectors. And so now to find the magnitude of the length of this vector, or the magnitude of this vector simply, we can just apply the formula. And what we get is that um, the length of this vector, let's just call it A, right? So A squared will be equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine of the angle. And what is the angle in this case? Well, clearly because we said that that the direction of the boy's motion changes by 60 degrees. So the angle over here, this angle theta, is actually 120 degrees. And so now we plug that into the equation. What we get is cosine of 120 degrees. And then we can calculate this value. Like these are all like numerical values. So we can simply calculate it and we can find that A will be equals to just some value here. And that's how we can add vectors. Basically, what we do is that we mathematically use the cosine rule, and by using that, we can find the magnitude of the summation vector of the vector that is like a summation of the other two vectors individually. And that is how we mathematically deal with vectors. All right, I hope that's understandable. Um, all right, and now with that covered, let's move on to the actual kinematics at hand. So as we've already like mentioned earlier, in kinematics, we have our different quantities um, of displacements, velocity, and acceleration. And we have already clearly explained that all three quantities are all vectors, that they all have direction and the magnitude. Right, so now let's quantify what exactly these three things are. So displacement, of course, it's the most easy to understand, as we've already mentioned. Displacement is simply a change in position. So for example, just now we mentioned the example of the boy moving, right? So the boy moves some distance in some direction, that will be considered a displacement, right? So let's say a boy moves 4 meters southeast. So a boy moves, let's say, 4 meters in this southeast direction. So this will be the displacement vector that points along this southeast direction with a magnitude of 4 meters. This will be our displacement. Uh, I think that should be quite okay to understand. Wait, sorry. And as for velocity, um, now we will introduce the concept of time. So basically, kinematics, we also study the motion of objects over time. So how the position of the object or like the velocity will vary over time, and that's a very important kind of like exploration into kinematics. And so what velocity is basically the change in displacement over change in time. And note that, right, velocity is different from speed. We know that speed, right, quite intuitively, is the change in distance over change in time. Let's say for some car moving along some highway, your speed will simply be the change in the distance traveled over the change in the time of like over the time period that the car is traveling in. So if your car moves 1,000 meters in let's say 10 seconds, okay, that's a bit unrealistic, but basically this means that your speed will be 1,000 over 10, which will be equals to 100 meters per second. This will be speed. But velocity is different. Velocity is different because it has direction. And that's something that we can't like I can't understate. Like direction is crucial in understanding kinematics. And why is that so? Let's just give an example of when speed and velocity are different things. So a classic example will be that of circular motion. Basically, let's say we have some object, some boy running along some track, for example. Let's say this is the track, right? And we have this boy here who is running along the track at some speed of like, let's say v, all right? So in this case, the speed of the boy will be constant, right? Speed is constant, correct? Because you can say that the boy is constantly running at the same speed because like it's covering the same amount of distance per second or per unit time. However, velocity is actually different. It's not just about the magnitude, but it's about the direction in which the speed points. So let's say at this point, if we say that the boy is running like anti-clockwise, then the velocity when the boy is at this point will be pointing in this direction. But after a while, when the boy is at this point, the velocity will actually point in this different direction. Of course, the velocities are all like perpendicular to the radius of the circle. So as the boy moves along this circle, its velocity actually changes because the direction of the velocity is changing. The direction of the vector is changing. So therefore, this means that the velocity is actually changing. So it's not constant. The velocity isn't constant. And why is this so important? To answer this, let's look at acceleration. So what is acceleration? Acceleration is basically, of course, velocity is change in displacement over change in time. So acceleration is basically just change in velocity over change in time. And now what does this mean? Let's go back to the example of the boy moving in a circle, right? So in this case, we've already established that your velocity isn't constant, right? Your velocity is changing because the direction of your velocity is changing. So therefore, your acceleration, which we defined already to be the change in velocity over change in time, is actually not zero, right? Because the velocity is changing. So therefore, your acceleration has to be present to cause the velocity to change. And what does that mean? Why is that so important? Because if you think about speed only, right? If we define acceleration to be the change in speed over the change in time instead, because the speed is constant, that will mean that your acceleration technically should be zero because like if you define it that way, then your acceleration will be zero. But the thing is, it's not because the direction of the velocity is changing. Therefore, this means that there has to be an acceleration to cause the velocity to change. And this concept is actually quite crucial because we will learn later that there's this thing called the centripetal force. So what this force is that we know that later we will learn that force creates acceleration related by your F equals to ma. Basically, your force, right, that you apply, let's say you push or pull a block, is equals to the mass of this object times the acceleration of this object. So this is a crucial relation. And basically what this implies is that because your object in a circular motion has a non-zero acceleration, therefore this acceleration needs to be provided somehow by some external force. And therefore what this means is that for any object to move in a circular motion, it needs to be supplied with this force, this centripetal force, to give it the acceleration required to move in a circular motion. And so that's why direction is so crucial because even though the speed doesn't change, the velocity or the direction of the speed will be changing. Therefore, there will be an acceleration, and this acceleration needs a force um, to provide it such that your object can actually move in a circular motion. And so this is why we keep emphasizing that direction is very crucial in kinematics. All right, so just to summarize again, our displacements is your change in position. Velocity is change in this displacement over the change in time. And the acceleration is a change in velocity over change in time. And again, these quantities all have directions associated to them. So therefore, they are vectors and not simply scalars like your distance and speed. So this difference is quite important, as you saw in the circular motion example, where your object can have a constant speed, but a non-zero acceleration, which requires a centripetal force to provide for it. And so, therefore, that will be all of the kinematic quantities that we will discuss, displacement, velocity, and acceleration. And now with all of these concepts in mind, we can move on to talk about the actual mathematics. Like how do we mathematically relate these three different kinematic quantities? And so that will be our next part for today. So what we will discuss now is what we call the suvat equations. And what is suvat? The S in suvat stands for displacement. It's basically like the mathematical symbol for displacement. U stands for the initial velocity of the object. V stands for the final velocity of the object. A stands for acceleration, and T stands for time. So these are the quantities that we'll be concerned with. Your displacements, initial velocity, final velocity, acceleration, and time. Of course, here we have an initial velocity and final velocity because your acceleration will cause your velocity to change over time. So that's why we have to make this kind of like this differentiation between your initial and final velocities. And now how do we quantify the relationships? So firstly, in these equations, we shall assume that your acceleration, right, is actually constant. So basically, this means that your acceleration points in one direction with a constant fixed magnitude of, let's say, A. So the direction will not change, the magnitude of the acceleration will not change, which means that your change in velocity over change in time will also be constant. And so that is the assumption that we will make in the following equations. Furthermore, to simplify things further, we only consider one directional motion. So basically, we consider the motion of the objects in one line only. Like your object can move forward, your object can move backward, but it can't move like, let's say, up or down. So basically, this simplifies things because the only direction that we need to consider will be left and right along this line itself. Your object will like move along this line, will accelerate along the same line, and will only be displaced along this line instead of any other direction. So with this in mind, let's move on to first talk about some important concepts. So how do we quantify all of these relations and how do we relate them to each other? Well, one thing very important to note is actually that if you plot a graph first, right? Let's say we plot a graph of acceleration against time. So what this graph will look like would actually be a straight line, right? A horizontal straight line. Because you have said that your acceleration is some constant. So acceleration over time will also be constant, right? So this is the idea of like an acceleration time graph. And we can also plot velocity time graphs, right? Um, velocity time graphs will be a bit different. And we're unsure how it looks like yet because we have to like derive it later in our equations. But we can also plot velocity time and displacement time graphs for like basically like all of these kinematic quantities. And so now a very important idea is this, that let's say we have the acceleration time graph, right? How do we find the change in velocity? Like delta v, the change in velocity. How do we find this value graphically? The idea is that the change in velocity will actually be equals to the area under this acceleration time graph. A change in velocity corresponds to your area under the acceleration time graph. All right, so why is this so? We will first analyze it using some intuition. Okay, so basically, let's just say we have some arbitrary kind of graph, okay? Like the shape isn't really important. It can be any type of weird ass acceleration time graph. So let's just like say it's some random curve like this. Mm. And what we can consider is that we consider this small time interval. Delta t. So let's just say we cut a slice here, a small thin slice here. So like the time here, let's say is t0. Then the time here will be t0 plus delta t, right? And if I ask you what this area is, like what does this small infinite small area represent? The answer would be that, of course, we know that this length here, this side of the rectangle here that we have, has a length of a. Basically, your acceleration at this time t. So like if you define your acceleration to be a function of time, then what we have is that at this time, the length of this rectangle is actually your acceleration at the time t0. And we know that the width of this small rectangle is actually delta t, right? Like this is the definition that we are trying to find, like we're trying to consider like this small time interval in which your object is accelerating. And so in this case, what this area will be, the area of the small region will actually be equals to your length times the width, right? So it will be your acceleration at the time t0 multiplied by your infinite small time interval delta t. And this will be your area in that time. But like what we actually know, right? What we actually know is that your velocity, right, or a change in velocity is actually defined to be your acceleration times time, because you know that your acceleration, right? Your acceleration is actually equals to your change in velocity over change in time. Like this is how we define our acceleration. And so what this means is that your acceleration times your time, your infinitesimal like small time interval will actually be a small change in velocity. So what this means is that in this time interval, delta t, right? Like in this time interval delta t, right? Your object will be moving, will increase in velocity delta by delta v. Wait, sorry, let me just repeat that again. Basically, in this time delta t, your object's velocity will change by delta v equals to your acceleration at that time times delta t. And what we can do is that we can sum all of these infinitesimal areas, right? So we can just take, for example, this small area here, this area here, basically all of the small infinitesimal areas under this like graph here, and sum everything up. So you sum all of these areas together, and what we will actually get is that the sum of these small change in velocities will correspond to the sum of these small areas, because these a delta t's are actually the small vertical areas. And so therefore, eventually what we get is that the final change in velocity, or the total change in velocity, actually corresponds to the total area, right? Because what we know is that each small infinitesimal change in velocity corresponds to an infinitesimal vertical piece of the area of the area under the graph. And so therefore, if we sum everything together, then the total change in velocity will be equals to the total area of all of these small rectangles, which will be equivalent to the total area under the graph. So it will basically be this entire area. And therefore, this leads us to a conclusion that your change in velocity will be exactly the area under the acceleration time graph. And this idea also applies to displacement and velocity, that your change in displacement, or in this case, just a displacement, your displacements, right? Your displacements will actually be equals to the area under the velocity time graph. And why is this so? Because it's the same relation. Your velocity is a change in displacement over change in time, and your acceleration is a change in velocity over change in time. So it's the same kind of like time relation that relates your velocity and displacement as well as the acceleration and velocity. Therefore, this same idea of the area under the graph being the change in a value will apply to velocity and displacement too, not just acceleration and velocity. So therefore, the same thing applies that if um if we have some arbitrary velocity time graph, right? Just some random shape, then this area under the velocity time graph will actually be our displacement. So this idea here is actually quite crucial for us to understand our suvat equations later. So just to repeat again, your change in velocity will be the area under the acceleration time graph. And I'm sorry, your change in displacement will also be the area under your velocity time graph. And so with that in mind, let's move on to do some math. So again, let's emphasize again the assumptions. We have a constant acceleration as well as motion along a straight line. So again, let's just draw the acceleration time graph again, right? And now we know that the change in velocity will be the area under this acceleration time graph. So we can simply write that your change in velocity will be this area. And what is this area actually? It's quite clear that because like your acceleration time graph is simply a straight line. So therefore, the area under this graph will just be a rectangle, right? This is simply a rectangle. So geometrically, your change in velocity will simply be the acceleration, the constant acceleration, multiplied by the time of acceleration, right? So this will be a change in velocity. However, if we have an initial velocity u, then that means that your final velocity v will have to consider both the initial velocity and the change in velocity. So this will be our first equation, that your final velocity v equals to your initial velocity u added to the change in velocity, which is the area under the acceleration time graph, at. So this will be our first result for today. And now with this in mind, we can actually plot the velocity time graph, right? Now we have the equation for velocity against time. Like we know like the relation between velocity and time. So we can also plot out a velocity time graph, velocity against time. And how do we plot this? Like it's quite clear from this equation, right? That your velocity is linearly related to your time, right? With a gradient of a. So what we can do here is that we can just simply plot a line here going up, uh, that starts at u. Your initial velocity is u, and it accelerates over some time t, right? And over here, it is at some final velocity of v. So this is our velocity against time graph. And of course, it's a straight line because your gradient is your acceleration, and your acceleration is constant. So that's why we're able to obtain this graph. And as we already claimed just now, your displacements will actually be the area under the graph, right? So it will be this area here under the velocity time graph. And now how do we determine this area? So firstly, a way to visualize it is that we can divide this area into a rectangle as well as a triangle. So of course, we know that the area of this rectangle, because the length of this side is u, and the length of the other side is t. So therefore, the area of this rectangle is simply ut, right? U times t. And as for this triangle here, it's a right triangle. So the area will be half times the base. The base is also of length t, multiplied by your height. And your height is of a length of, because your change in velocity is actually a times t, your acceleration times time. So therefore, this length is also at. And so we multiply this by at, and our final area, or your final displacement, is actually ut plus half at squared. And so therefore, our equation is that our displacement will be your initial velocity times time plus half of your acceleration times time squared. And it is through like this sort of like graphical method that you can understand why you have like these things. Like for example, you have a half here. Like a half appears because and the half here appears because you have a triangle. And your triangle's area is half times base times height. So that's why your half comes in. And of course, dimensionally, right? If you think about it, the acceleration has units of meters per second to the power minus 2. So therefore, that's why you have time squared, like multiplied to it. You multiply this by second squared, and you will obtain meters, which is a unit for displacement. So this will be our second equation that we can obtain. And our third equation that we can actually obtain, right, is that if we consider this, like find the area in a different way. So what we can also do is that we can find the area by considering, like if you draw a line through the velocity time graph like this, and we say that like this line is in between, like it intersects the midpoints of this line here. So this means, what this means is that your line will have a velocity of u plus v over 2. It's basically like the average of your initial and final velocity. And this area here, like this area of this particular rectangle here, is actually equal to the area of this trapezium, right? Because the area of this segment here is equal to the area of this segment here. So you can visualize shifting this area down to this part here and creating this rectangle of a length of t and a height of u plus v over 2. And so therefore, we can say that our displacements can also be written in this form. So like u plus v over 2 is what we call the average velocity. Which is basically the average, okay, like the average velocity is basically the change in displacement, like over change in time. But as in like, because it's over a longer period of time. So like your velocity is your instantaneous change in like your instantaneous change in displacement over change in time. So it's like over a very small period of time delta t, your displacement changes by a very small amount delta s. And this is called your instantaneous velocity. But the average velocity will be your like basically how fast on average object moves. Like in this case, like your velocity changes, right? So what it's simply saying is that it's the velocity that we can prescribe the motion. If we like it's the equivalent velocity that allows your object to move the same displacements if there was no acceleration. So in this case, your average velocity is simply u plus v over 2. And therefore, our third equation is simply that your displacements is related to both your initial and final velocities. All right, and now what we have is that we have three equations. Let's just write out all these equations somewhere else. So our equations are that v equals to u plus at, that s equals to ut plus half at squared, and s is also equals to u plus v over 2 times your time. So these are our three equations. And actually, we can have one more equation. If we combine these three equations and do some math, what we can get is that v squared equals to u squared plus 2as. So this is actually our fourth equation that we can derive mathematically from the other equations. And so in the end, what we have is that we have these four equations. These are the suvat equations, which describe the motion of an object. And with these equations, we can go on to solve different kinematic problems and understand the motions of objects better. So just to repeat again, S is displacement, V is velocity, your V is a final velocity, U is an initial velocity, A is an acceleration, and T is a time. So these will fully describe your displacements, your velocity, and acceleration over time. And just to summarize again, we can derive all of these equations by considering the areas under the different curves, because you know that your change in velocity is the area under the acceleration time curve, and your displacement is your area under the velocity time curve. Right, so I hope that you guys were able to follow that. And yeah, so that's basically the suvat equations. And so now let's say we want to apply it to solve some problems. Of course, a very classic problem is like, let's just say we have a ball, right? Let's say we have a ball, like which is initially on the ground. and we throw it upwards with some initial velocity u. So what is the maximum height? Let's say like the ball reaches some maximum height h. What is this maximum height that the ball can reach? Of course you know that's right. Like because we're on Earth, so therefore your ball is experiencing an acceleration downwards. This is our gravitational acceleration g, right? Your gravitational acceleration downwards. This is like the acceleration that every single object on Earth has downwards at the surface of the Earth. And its magnitude is, of course, 9.81 meters per second. Sorry, meters per second squared. And so now we have our constant acceleration, we have our initial velocity, and we want to find the maximum displacements or the maximum heights. So how do we do this problem? So of course we can look at our equations again. We have our suvat equations for the motion of the objects. So firstly, we can clearly see that your velocity of this ball will be equals to u minus gt. So firstly, why is it minus instead of plus now, right? Like just now we wrote in the equations that your v is actually u plus at. But why is it that in this case now your velocity is actually u minus gt? So the reason for this change in sign is because your acceleration is acting opposite to your velocity. So in this case, your acceleration is actually negative. Your g is pointing downwards. So relative to your motion, it's actually a negative value. And basically it decreases the velocity of your object because it's acting in a direction opposite to your velocity. And therefore, your velocity decreases over time, and it should be a u minus gt instead of a u plus gt. So this sort of like intricacies are very important. Like you need to know whether your object is being accelerated or decelerated, whether the velocity increases or decreases. And that will help you to like write out your equations more accurately so you won't make this sort of mistakes. Like because in this case it's a minus instead of a plus. So this means that of course your ball, right, as we intuitively know, if you throw a ball upwards, it will slowly come to a stop, then it will fall back downwards, right? So what is the point at which your object comes to a stop? Like this point is actually maximum height, right? Because you can imagine that your ball will go upwards, right? Then at this maximum height, it will stop moving. Then it will continue accelerating downwards. And then it will fall back down. So this maximum height here is actually the point where your v equals to 0, right? So v equals to 0 is the maximum height. And now we have this equation, right? We can use this equation to find the time at which your velocity is 0. So if we do just some manipulation, you can see that u minus gt at this time where the object reaches the maximum height is actually equal to 0. And doing some math, we obtain that your time is actually your initial velocity u over your acceleration g. So this is our time. And now how do we find the maximum height then? We have that the time is u over g, and we know that the acceleration or the deceleration is g, right? So now we can use our suvat equations that our displacement is equals to, let's just use the second equation first, is equals to your initial velocity times time, u over g. And this case is minus, right? Because the acceleration is downward. So it's minus half times g times the time squared, so u over g squared. And we obtain that your displacement is half times u squared over g. And this will be a maximum height of the object in this motion. And of course, our equations can be used quite flexibly. We can also use the idea of average velocity, where our displacements will simply be the initial velocity u plus the final velocity, which is zero, right? Because that's the maximum height. The maximum height is when the velocity is zero. So plus zero divided by two, multiplied by the time of the motion, which is u over g. And so you obtain that your displacement is u squared over 2g. And this is the same as what we obtained from the other equation. And lastly, we can also apply our final equation that we say we can derive. So it's this equation, v squared equals to u squared plus 2as. So we sub in the values. Your final velocity v is 0. So 0 equals your initial velocity u squared plus 2, oh sorry, it's minus because your acceleration is downwards and negative. So it's minus 2 times your acceleration g times displacement, which will be, in this case, h, because this is a maximum displacement. And so therefore, if you again do your math, your h will again be u squared over 2g. And these three results will all correspond to each other. So through three different methods of using the suvat equations, we can obtain the same result three times. And yeah, this shows that our equations are actually correct and they're consistent with each other. And this is quite nice. So in suvat, right, by like with suvat equations, you're actually given a lot of flexibility that you can use like whichever equation is more straightforward for you and more easy to deal with. And in this case, actually using this equation here, v squared equals to u squared plus 2as, this equation here is actually perhaps like arguably the most convenient. Because like in the other two equations, you kind of like needed to calculate the time first, right? Like both of these needed to calculate time. But in this final equation, we already know everything. We know the final velocity at the maximum height. We know the initial velocity. We are given the initial velocity. We are given the acceleration, and we want to find this displacement or the maximum height h. And so therefore, like it's very straightforward. It's simply one equation, and you can get the result directly. And so yeah, you can just shift between your different suvat equations and figure out which one you want to use in different scenarios. All right, so I think that's everything for today's lesson. We've covered quite a bit. So let's do a quick summary first. So in kinematics, as we have already mentioned, um, we have our various quantities. Um, we have displacements, velocity, and acceleration. So S, V, and A. So the velocity is a change in displacement over change in time. So the idea of time is also very important. And the acceleration is change in velocity over change in time. And we know that all of these are all vectors, which have magnitude and direction. And we learned that we can sum vectors. So let's say we have two vectors like this, and we want to find the resultant vector like this. So we can sum two vectors like this through the cosine rule, which we stated already earlier. And so this is how we can sum vectors. And the direction of the vector is also very important in the calculations, which can be defined by these angles, right? So yeah, that's vectors. And we have our suvat equations. So again, like S is like displacement, V is velocity, A is acceleration. And in this case, a U is initial velocity, and a V is the final velocity. And so our equations are again V equals to U plus AT, S equals to UT plus half AT squared, also equals to U plus V over 2 times T, using the idea of average velocity. And lastly, we also have our more special equation, which is that your V squared equals to U squared. plus 2as, which we can derive from the other few equations that we are given, that we have derived by ourselves. And again, the key idea here to solving these equations, to deriving these equations, is that you consider the area under the different curves, right? So if you remember, the area under the acceleration time graph is the velocity, and the area under the velocity time graph is our displacements. And so this allowed us to derive firstly the velocity from acceleration, and finally the displacement from the velocity and acceleration. And so therefore, this is a summary of everything we've done today. In our next lesson, we'll probably move on to talk about more difficult concepts such as um, two-dimensional motion. So we will talk about projectile motion. We will talk about using calculus. This is more advanced, so if you aren't familiar with this mathematical tool, then it's okay also, but we'll also cover it slightly to give us like a better understanding of kinematics. And lastly, we will also like just do more problems. We will try and attempt to use these equations in different scenarios. And yeah, so this is basically the end of our lesson. Thank you for listening to this lesson. I hope that the pace was okay and that I explained things all right. Again, if you have any feedback, just contact us. We'll be more than happy to listen to what you have to say. And yeah, so that's the end of the lesson. Thank you for listening, and I hope you guys have a good day.